This is another 2023 number challenge. We look at harmonic series with certain terms removed. That is the term that contain 2023 digits. So if a number n, natural number, if the base 10 representation as a string contain 2023 as a substring, we would exclude that in the summation. So what is the first term that we skip? So we're going to go from 1/1, 1/2, and up to 1/2022. Then we're going to skip 1/2023. The next term here is going to be 1/2024. And then we go on just like the typical harmonic series. However, we're going to skip 1, 2, 0, 2, 3 next, and so on and so forth. Now, it turns out that this kind of problem was raised back in 1914 by Kempner. So he figured out that for the series, if we remove all the terms contain certain single digit d, here d would be from 0 to 9, right? Then this series actually converges. Was quite surprising. So k sub d here is that we're going to remove digit d. Now, for example, if d equals 9, what we're doing here is we're going to remove from the harmonic series all the digits that contain 9. For example, when we have 1/8, we're going to skip 9, 1/10. And then when we go 1/88, we're going to skip 1/89 because it has 9 there. And then we're going to skip 90, 91, 92, up to 99. The next number is 1/100. All right. So there's a few observations. First of all, how many terms we have removed from the original series in this case? Of course, we removed infinitely many terms, and how many are remaining? Also infinitely many. So that is, we have removed infinitely many terms, and we still have infinitely many terms left. Okay, so does it converge or not? Because if terms are left are finite, then of course it's a finite number. And if we remove only finite number of entries, the original series diverges. If we do remove finite number of entries, then the remaining series will still diverge, right? But in this case, we have removed infinite many. But how many exactly, right? So when I first look at this problem, my intuition tells me that maybe because we're removing digit 9, right? Anything contain digit 9. Maybe it's about 1/10 because there are 10 digits and we only exclude 9, right? So maybe 1/10 or 1/9, somewhere in between. Let's see if our intuition is correct. All right. So let's do some math here. How many are removed? This is something we need to first look at. Now in this case, let's consider 100 digit numbers. Among those numbers, how many are kept in K9, right? So first of all, how many numbers are there for 100 digits? For the first digit, it's going to be 1, 2, up to 9, so 9 choices. For the remaining digits, you could have 0 to 9, 10 different choices. So the total possible numbers is going to be 9 times 10 raised to 99th power. It's a huge number, right? But how many are kept in the K9 sequence? We want to exclude all numbers that contain 9. So that is, the first digit is going to be 1, 2, up to 8. So 8 choices. And the remaining digits is going to be, because we're going to construct 100 digit numbers, right? In base 10 decimal representation, right? So each remaining digits would have a choice of from 0, 1, up to 8, 9 choices. So what we have in K9, we only take about 8 times 9 raised to 99th power. Now, what percentage are kept? So the 1 minus the percentage would be what percentage that we have removed. So we look at how many we have removed. It's going to be 1 minus the ratio of this, right? Notice, however, 9 over 10, 0.9, less than 1. If you raise to 99th power, the number is getting smaller and smaller. It's tiny, right? How tiny is that? It is about, we have removed almost everything, okay? So we have removed 99.997% of numbers among all 100-digit numbers. That's quite a contrast to our original intuition that we have removed about 1/10 of numbers. Okay, this just tells us that we are not, as a human mankind, comfortable with intuition with big numbers. Okay, so if you learn multi-calculus, one thing you're gonna learn is that for the higher dimension, if the dimension is huge, and then what is the unit ball in that dimension, right? There are some counterintuitive conclusion there. Now here is the same thing, right? So when we first look at this, the percentage, now there's no way we would, from my basic intuition that we have removed almost everything from the sequence, okay? Even though we say we're going to exclude only digit 9 in all the integers, okay? And another question I raised to you is, you can say the same thing, for 1, for 2, and things like that. But then we're not add up to 1, right? Because we have removed everything. We only kept, less than 0.003% of numbers, right? So anyway, let's go back to the original question. We claim that K9, as a matter of fact, KD for other digits is also converges. Why is that? That is the case. Okay, let's look at that. So for those 100-digit numbers, what is the total contribution to this 1 over n series, right? So let's do some analysis here. Yeah. So we claim that KD converges, including K9, right? And why that is the case. Okay. So the total terms for n digit, using the earlier analysis is going to be this, right? This is the term that we kept. And for each n digit, 1 over that n, and not n, 1 over that number is going to be less than 10 raised to, n minus 1, right? So basically, because the smallest number is going to be 10 raised to n minus 1. And so the maximum possible value for those terms in the n digit is going to be 8 times 9 n minus 1 divided by 10 n minus 1. And then, so the whole sequence here is bounded above by this summation from the, the number of digits from 1 digit to 2 digit to infinity, right? So notice that this is a geometric sequence. The ratio is less than 1, so it will converge. So that is, we have found an upper bound. What is the upper bound? So this is going to be, this part is constant, and this part, as n varies, is a geometric sequence, so it's add up to 10. So the total number is 80. So that is bounded above, and the sequence, of course, as we go on, is strictly increasing, okay? For a sequence that is strictly increasing and bounded above, and it should converge. So K9 converges, okay? So this Kempner had this finding back in 1 century ago, okay, 1914, all right? So let's look at our original problem. Original problem is similar, but actually, before we do that, let's go back for this actual results of this, right? So if you check out on the internet from MathWorld, this is the result. For KD, which is a series removing the digit K, digit D here, and if we remove 0, it converges to this number, 23. And if we remove 9, it converges to 22. So everything is centered around 22 ish, right? So that is the D, removing a single digit case, right? That's the result. Now let's go back to our original question here. Now here we are removing maybe less terms, right? So we would like to do the similar analysis. We're going to ask ourselves, how many terms are removed? Yeah. So here, of course, the first term we removed is 1 over 2023, and the next one is going to be 1 over 12023, and the next one will be 20230, 20231, 20232, and so on and so forth, right? So intuitively, we have removed less than KD if we remove only the digit 9, right? So we remove a lot of more entries here. Now, but here, same thing is true. We have removed infinite many terms, and then we have left with infinite many terms, all right? So does it converge? Okay, so we want to do similar analysis, maybe try to find an upper bound, right? So how would you do that? So maybe we try to do similar analysis, right? How many numbers are included or how many numbers are removed for n-digit numbers? Now this time for the n-digit, how many of them that does not contain 2023 as a subsequence? That's a counting problem. There must be an answer, but the analysis is not as straightforward as the one we did for K9, right? Now let's review what we did in K9. Okay, so here we are saying that the n-digit number, when we say n-digit number, we're talking about base 10, of course, right? So base 10 n-digit, the total number would be this, right? And we're saying what the term that we have included in K9 is going to be this. Again, this is base 10, okay? So what if we say the base, a higher base? Let's say if we would include the number in base 10,000. So in that case, 2023 would become a digit, right? So for example, D in that case would be a digit in that base, right? Let's go back. In the KD, here's the notation, we say K9 because 9 is what? Is a digit in base 10, right? And there are only what? 10 digits, all right? So that we have this, expression here. So there's nothing special about base 10, right? So you could argue that for base B, this 10 would become B raised to the n minus 1's power for the n-digit number in base B, right? For other base, right? And this is the same thing, same analysis. So in other words, it may be easier, or maybe if we apply this sort of analysis for K9 in base 10, but if we were to choose a bigger base, a base 10,000, even though usually we don't do that, usually we're dealing with like binary base 2, hexadecimal base 16, but here for its convenience, we want to use base 10,000, right? In that case, 2023 will become a digit, okay? So KD in that base, if we remove all digit 2023, okay? So that's it. That is, as a digit in base 20 and 10,000, we're gonna skip 1 over D. D is a digit, single digit, okay? In that base, the huge base, right? So the question is this new sequence the same as our original sequence that we're gonna exclude 2023? The answer is no. They're not the same. Why? Okay. So for example, for the two sequence, all these are skipped in both, right? So because the first number, of course, in the base 10,000 is going to be 1 over D, and this is going to be 1D, right? Is a symbol for 2023, and this is going to be D0, right? So those are removed in KD and also in our original, series S. However, for some other numbers, like for example, 20230 is skipped in our original sequence, but in KD, in this notation, it is kept because this 0230 is going to be one digit. Let's say digit A, right? So the representation in base 10,000 is going to be 2A. So KD would include that entry. So in other words, KD intuitively contains more entries, maybe much more entries than our original sequence. But even with that, in other words, this is bigger, the summation would be bigger, right? Does it have a bound, upper bound? Of course. The answer is yes. The analysis would be identical to the one that we did for K9 earlier in base 10. All right, there's nothing special about base 10. So in base 10,000, we make the same argument. In base 10,000, right? So that's our kind of steps. So we first argue that as our series has fewer terms than KD in base 10,000, right? And the missing term in KD is a subset of the missing terms in S, all right? In other words, KD removed fewer items, right? And we want to argue that KD in this notation here still converges, right? So why that is the case? The argument is the same, is identical to the one we did earlier. That is, if we know KD converges, then S must converge, right? But let's just review what we did for K9, right? We said for the n digit in base B would have this many numbers, right? B minus 1, B m minus 1's power. Same argument. And the number that we included in this here, because we have removed many, and it's going to be B minus 2, because we're not going to use digit 2023 is a digit here, right? We're not going to use digit D. So we have this many. And each one contribution to the harmonic series is bounded above by 1 over this thing, right? Because we're talking about base B. B is 10,000, by the way. Yeah? So that is for each term, right? So in this expression here, the key here is that no matter how big the B is, this is less than 1, all right? Earlier we're dealing with 9 over 10, but this time we're dealing with 999, 4 nines over 10,000, right? Still less than 1. So if you raise to higher power, it's going to be tiny, right? So in other words, as we go with like 100 digits or 1000 digits, we include very tiny portion of the original harmonic series. We have removed almost every numbers, okay? And the summation again is this geometric sequence here, and this would converge to a constant. This is a constant, right? And so the bounded above by a bigger upper bound, but still it is a finite number. This is all matters, right? So that is KD is bounded above, KD is strictly increasing, KD converges, right? So that we have the conclusion, and for our original sequence, is also converged because it's smaller, remove less than the KD in the notation here, and there is a paper, you can find out from the reference here that the value is approximately this, okay? And the author also provided a mathematical code for actual calculation, so that it has more digits, right? So it's about 23,000, okay, for this sequence S as we defined. And notice that this convergence, including the KD, is extremely slow. So if you try to estimate maybe partial sum, you're not going to get anywhere close to the numbers, even for the K9. And in this case, you can try maybe many terms, maybe 1 billion terms. Still not the difference to the conversion value is still greater than 1. In summary, when we look at this sequence by excluding all integer n that contains 2023 as a substring, we argue that for the Kempner series in base 10, KD, for example K9, converges. Now we use similar logic, but this time when we look at base 10,000, KD also converges, and in particular K when d equal 2023 as a digit in that base also converges. And we further argue that S has fewer terms than KD or K 2023, so it also converges. All right, so that's overall thread of reasoning here. I have a series of other 2023 number challenges. Do check them out, and I have the video link in the video description below. Okay, in the meantime, please like, share, and subscribe to the channel.